Hello everyone, in this video we will go through review notes for chapter 7. Target parameter is usually a noun and it refers to a population parameter. It can be a mean or proportion that we're interested in estimating. Also, point estimator is a rule or formula that tells us how to use the sample data to calculate a single number that can be used as an estimate of the target parameter. We basically use the point estimator to estimate the population parameter. And confidence interval, or also same as interval estimator, is a formula that tells us how to use the sample data to calculate the interval that estimates the target parameter. Confidence coefficient, which usually is defined in confidence level, with the confidence level is the probability that an interval estimator encloses the population parameter. That is the relative frequency with which the interval estimator encloses the population parameter when the estimator is used repeatedly a very large number of times. In table 7.2 in the book, that would be here we have confidence level at different percents, 90% to 99%, and the corresponding z at alpha over 2. And here it will be very useful to keep these numbers and values in mind. Where at 90% confidence level, we can have the z alpha over 2 as 1.645, and at 95% we'll have z as 1.960, and 98% as 2.326, and 99% at 2.575. By increasing the confidence interval, we can see the z is getting bigger, which means it's actually increasing the interval of the confidence. Sampling distribution of mu. Depending on sample size, we can calculate sampling distribution of mean. Here we have two different sets of formula where we can use for large samples and small samples. If sigma is known, we can simply use this formula. Where sigma is unknown, we can simply calculate the sigma using s over square root of n. Also, when our sample is small, we consider n bigger than 30 as large and n less than 30 as a small sample. And basically, due to central limit theorem, this condition guarantees that the sampling distribution of X is approximately normal. Also, when sigma is unknown, we can again simply calculate using S over square root of n. Here we can use this formula at three conditions. When sampling distribution when the sampling is totally random, or a random sample is selected from target population, where it's selected randomly. For large sample, as I mentioned, we consider n bigger than 30, and the population, and for small sample sizes, the population has a relative frequency distribution that is approximately normal. This has to be met for small sample distribution. when calculating confidence interval for mu. We can also get the sampling distribution of proportion. Again, we can have a large sample or a small sample size. When we have large sample, we mean n times p hat greater than 15. We can use this formula, both n times p hat and n times q hat. Where p hat equals x over n and q hat is 1 minus p hat. Also, when n times p hat is less than 15, or n times q hat is less than 15, we can still get the confidence interval for a population proportion using adjusted form, where we basically calculate the p tilde using this formula. Also here, for sampling distribution of proportion, like I said, we have conditions to met. We have conditions to be met. First of all, just like sampling distribution of mean, samples has to be picked randomly from the target population. Also, the sample size is large, and we can use large sample confidence interval when NP is bigger than 15, and also NQ bigger than 15. Relationship between sample size and width of confidence interval. We can get the n. We can also calculate the n using sampling error, which is basically z at alpha over 2 times sigma over square root of n. Is basically this part of formula where we saw here that cause the interval goes wider or smaller. Here we can see an example where we have n as 100 and n becomes 983. We can see the SE value from 0.78 decreased to 0.25 by increasing the sample size or making SE smaller and interval also smaller. Same as proportion, we can calculate the SE using the second term of the formula. And we can get the minimal, or the best sample size using this formula. Thank you so much. We'll see you in the next video.